Hello everyone. In this video, I will be discussing my solutions to the AP Calculus BC 2012 Practice Exam Multiple Choice section. As a note, I do not own any of the questions below. They are the sole property of the College Board, who does not endorse this product. I will be presenting my own solutions to this exam. And with that, let's begin on the no calculator section of the multiple choice section. To begin, consider the following. If y is equal to sine cubed x, then what is dy dx? Well, to start, let's take the derivative of y. To do this, we see that we have a sine cubed. Y can be written as sine x to the third power. So this then is reminiscent of the chain rule. So dy dx is 3 times sine squared x. So we bring down the 3, we make it a 2, and then we multiply by the derivative of the inside of the parentheses here. So the derivative of sine is cosine, so we multiply by cosine x. So dy dx is 3 sine squared x cosine x. So the answer is E. Next, consider the position of a particle moving in the xy plane to be given by the parametric equations x of t is equal to t cubed minus 3t squared, and y of t is equal to 12t minus 3t squared. At which of the following points, xy, is the particle at rest? Well, for the particle to be at rest, the velocity in the x direction and in the y direction both have to be 0. So we have to solve for the velocities in the x and y direction. We're already given the positions in the x and y directions, so the velocities are just the time derivatives of these equations. That is, the velocity in the x direction, v sub x, as a function of t, is equal to the time derivative of x. Then, taking the time derivative of x of t, we get that this is 3t squared minus 6t. And we want this to be 0. In solving this equation, we see that it has solutions t is equal to 0, 2. So it can be either 0 or 2. Similarly, looking at the velocity in the y direction, vy of t, this is equal to the time derivative of y of t. And looking at y of t, the derivative is 12 minus 6t. And we want this to be 0. The only solution to this equation is t is equal to 2. So we see immediately that there's a single shared solution to these two equations. So the time at which both velocities vanish is t is equal to 2. But this question asks for the following xy points for which the particle is at rest. To compute this, we simply have to plug in t is equal to 2 into x and y of t. Doing so, we find that x of 2 is equal to 2 cubed minus 3 times 2 squared. And this is 8 minus 3 times 4, which is equal to 8 minus 12, or negative 4. And y of 2 is equal to, looking at the equation again, 12 times 2 minus 3 times 2 squared. And this is equal to 24 minus 3 times 4, or 24 minus 12, and that's equal to 12. So the x and y points at which this particle is at rest is given by Negative 4, 12. So the answer is A. Moving on. The graph of f is shown above for 0 is less than x is less than 4. What is the value of the integral from 0 to 4 f of x dx? Well, geometrically, we know that the integral here should be the area under this graph from 0 to 4. So what I shade in blue has positive contributions to this area, and what I shade in orange has negative contributions. As a note, it doesn't matter that this point here is open and that these 2 points at x is equal to 2 don't match. All that matters is that you draw a line directly onto the x-axis and then you shade the region underneath this line. Then, computing the area of these two quantities, we have, well, the orange area is easy to compute. It's just a rectangle. Specifically, it has side lengths of 2 and 3, because this goes down to negative 3, and this is 4, and this point here is 2. So we have a rectangle of side lengths 2 and 3. So we have that the area is 3 times 2, or 6. And looking at this object here, we can split this into two shapes that we already know. Firstly, a rectangle, which has side lengths 1 and 2. So the area here, we already know that this bottom rectangle has an area of 2. So we have 2 plus the area of this triangle. Well, the area of a triangle is 1/2 times the base, which is 2. So 1/2 times 2 times the height, which is 4 here. So the area of this object is 2 plus, well, the 1/2 and the 2 cancel, so 2 plus 4. Then we see that this is 6. So the total area underneath this plot is given by, so the integral here from 0 to 4, f of x dx, is equal to, well, it's 6, the positive contribution, minus the negative contribution, which is 6. So the answer here is 0. There's no net area under this plot. So the integral here is 0. So the answer is B. Moving on, which of the following integrals gives the length of the curve y is equal to ln x from x is equal to 1 to x is equal to 2? To answer this, recall that the length of a curve L is equal to the following. The length L is equal to the integral from a to b, where a and b are the endpoints of this curve in question, and it's the integral of the square root of 1 plus y prime squared dx, where y of x is the curve in question. Here, y of x is equal to ln x. So y prime of x here is equal to d dx acting on ln x. But the x derivative of ln x is equal to 1 over x. So the length is equal to the integral from a to b of the square root of 1 plus 1 over x squared dx. So the answer here is B. Next, the Maclaurin series for the function f is given by f of x is equal to the sum from n is equal to 0 to infinity of negative x over 4 all to the n. We wish to find the value of f of 3. To do this, we first note that when x is equal to 3, f of 3 is equal to, moving this over, it's equal to the sum from n is equal to 0 to infinity of negative 3 over 4 to the n. But the absolute value of negative 3 over 4 is less than 1. So this is actually a geometric series. So it's a geometric sum. Then we know that the value of this sum from 0 to infinity is given by the following formula. It's given by, firstly, note that there's no coefficient out front, so this is 1. Because sometimes there might be an a in here, but there is no a. So the sum is equal to 1 over 1 minus r, where this whole quantity is equal to r. So plugging in for r is equal to negative 3 over 4, we find that f of 3 is equal to 1 over 1 minus negative 3 over 4. So it's equal to 1 over 1 plus 3 over 4. But 1 plus 3 over 4 is equal to 7 over 4. So this is equal to 1 over 7 over 4, or 4 over 7, which is our answer. So the answer here is 4 over 7, or C. Next, using the substitution u is equal to x squared minus 3, the integral from negative 1 to 4 times x squared minus 3 to the 5th dx is equal to which of the following integrals? Well, using this substitution, we first see that this part of the integral inside of the parentheses is just u. Then we take the derivative of this substitution here. That is, we take du dx. This is equal to 2x. This implies that du is equal to 2x dx. Then x times dx is equal to 1/2 du. But we already have an x times dx within the integral. So the integral can be rewritten as an integral of u to the 5th times 1/2 du. However, this is now an integral over u. So the bounds of the integral before were in terms of x. So we have to plug in for the new values. Doing so, we find that for u of negative 1, this is equal to negative 1 squared minus 3. So this is equal to negative 2. And u of 4 is equal to 4 squared minus 3. This is equal to 16 minus 3, which is 13. So the bounds on this integral are negative 2 and 13. So the answer here is C. Next, if arc sine of x is equal to the natural log of y, then what is dy dx? Well, taking the x derivative of both sides of this equation here, we find that, well, first let's take the x derivative of both sides. So d dx of arc sine of x is equal to d dx acting on the natural log of y. Then the derivative of arc sine is equal to 1 over the square root of 1 minus x squared. And the right-hand side is equal to 1 over y, because we're taking the derivative of a natural log, times the derivative of the inside, so times dy dx. Then, solving for dy dx, we find that dy dx is equal to y divided by the square root of 1 minus x squared. So the answer is A. Next, a tank contains 50 liters of oil at time t is equal to 4 hours. Oil is being pumped into the tank at a rate of R of t, where R of t is measured in liters per hour, and t is measured in hours. The selected values of R of t are given in the table above. Using a right-Riemann sum with 3 subintervals and data from the table, what is the approximation of the number of liters of oil that are in the tank at time t is equal to 15? So, underlining the important statements here, we're using 3 subintervals for a right-Riemann sum, and we're approximating the number of liters of oil that are in the tank. Not just the number of liters that are let into the tank, but the total number of liters of oil in the tank at t is equal to 15 hours. So, using a right-Riemann sum, we wish to use one that has 3 subintervals. So, to start, we have this table here. So our 3 subintervals will be 4 to 7, and then 7 to 12, and then 12 to 15, where for each of these, we use the right value of R of t. So for the first Riemann sum, the first term in the Riemann sum, we use 6.2 as the height of the rectangle. For the second one, we use 5.9. So this is the second term in the Riemann sum. And the third term in the Riemann sum is 5.6 as the height. So this is the third term. So the area under this plot, so as a note, R of t is a rate. So if we take an integral of it with respect to time, then we get the amount of liters that have gone into the tank after this amount of time. So if we want to find the amount A of oil that has gone into the tank, this is equal to, using a right-Riemann sum, 7 minus 4, because this is the first interval. It's the distance between 7 and 4, times 6.2. And then we add to that the second interval, which is 12 minus 7, times 5.9. And the third interval, which we add to this, is 15 minus 12. And we weight that by the height, which is 5.6. So this is the calculator section, the no calculator section of this exam. So even though we have these decimal places, we can't use a calculator. So we can do the next best thing, which is let's just make some approximations. So to start, we'll say that 6.2 is just equal to 6. It's close enough to 6 that we can call it 6. Then we'll say that 5.9 is also equal to 6. And we can do one of two things for 5.6. We can either call it 5 or 6. Or we can call it 5.5. Let's call it 5.5 here. We can also call it 6, but I'll call it 5.5. Then the amount of oil that has gone into the tank is equal to 7 minus 4, which is 3, times 6, plus 12 minus 7, which is 5, times 6, plus 15 minus 12, which is 3, times 5.5. So this is equal to 18 plus 30 plus 3 times 5.5. So the way that we can calculate this using shorthand is we can say 3 times 5.5 is equal to 3 times 5 plus 0.5. Then we can just distribute the 3 into both terms. So this is equal to 3 times 5 plus 3 times 0.5, which is equal to 15 plus 1.5, which is equal to 16.5. Then the third term here is 16.5. And adding these together, we get 30 plus 18, which is 48, plus 16.5, which gives us 64.5. But although 64.5 is pretty close to one of the answers, and since we approximated, all we want is an answer that's pretty close, this isn't the answer, because what it asks for is the approximation of the number of liters of oil that are in the tank. What we've calculated is the amount of oil that has gone into the tank. So the tank already has 50 liters in it at time t is equal to 4. So the total answer is going to be, deleting this, the total answer is going to be 64.5, the amount that has gone into the tank, plus the amount of oil that was already in the tank, which is 50 liters. So the total amount of oil in the tank at t is equal to 15 hours is 64.5 plus 50, or 114.5. And looking at our answers, that's pretty close to C, which is 114.9. So the answer here is C. Next, which of the following series converges? Let's look at each sequence in series. For 1, we see that we have a summand of 8 to the n over n factorial. Well, we know that for general n factorial is larger than 8 to the n. This isn't true for all n. In fact, if we choose n is equal to 1, we see that 1 factorial is equal to 1, which is less than 8 to the 1, which is equal to 8. So we already see here that for n is equal to 1, this inequality is incorrect. But for large n, say n is equal to 100, this inequality is certainly true. So we see that the summand here, in the limit as n goes to infinity, we see that the summand here goes to 0. And because n factorial grows so much faster than almost every other function that you'll see on the AP Calculus exam, whenever it's in the denominator, we can say that this series converges because it just grows so much faster than 8 to the n. So this sequence certainly converges. Next, let's look at 2. We have in the numerator now n factorial, and in the denominator we have n to the 100. So let's look at this integrand, this summand. We have n factorial, in general, is larger than n to the 100. And again, this is because n factorial here is the fastest growing function you'll see on the AP Calculus exam. So, although this inequality is wrong for the first, say, 100 n values, for some n, this is eventually correct. So, for some n value, all values above that n, this is true. So for large n, so in the limit as n goes to infinity, we see that this summand also goes to infinity. So the summand itself diverges as n gets large, meaning that the series certainly cannot converge. So this, number 2, does not converge. Looking at 3 now, we have 2 polynomials, one in the numerator and one in the denominator. So, as is always the case with these things, we take an asymptotic limit. So we say, what is the limit as n goes to infinity of this summand? Well, we can see already that if we take the limit of this thing here, we have n plus 1 over n times n plus 2 times n plus 3. But this thing goes as the limit as n goes to infinity of n to the largest power in that polynomial. So the largest power in the numerator is 1. So we have n here. And then if we factored all of this out, if we FOILed it all out, you would get an n cubed as the largest n power. So this goes as n over n cubed, which is equal to the limit as n goes to infinity of 1 over n squared. And this certainly goes to 0 as n goes to infinity. So we can see that the summand here goes to 0 as 1 over n squared. So this converges because we know that this sequence, or this series, from n is equal to 1 to infinity of 1 over n squared, we know that this converges. However, we also know that the sum from n is equal to 1 to infinity of 1 over n diverges. So, because this goes as 1 over n squared and not 1 over n, it converges. If we got rid of this n, though, then this would diverge. But we have an n here, so it converges. So 3 is also a convergent series. So the answer here is 1 and 3, or D. Moving on, consider the following integral. We wish to just compute this integral. So, to do this, we can take the integral of t to the negative 3 over 2. Well, when we do this, we get negative 2 times t to the negative 1/2. And we evaluate this from 1 to 4. And the reason that we know that this is the correct value is when you take the derivative of this with respect to t. So if we take d dt of negative 2 times t to the negative 1/2, the negative 2 can be pulled out, and then we do the usual rule here. So we pull down the negative 1/2, so times negative 1/2 times t to the negative 1/2 minus 1, or times t to the negative 3 over 2. The negatives cancel and the 2's cancel, so this is t to the negative 3/2, which is exactly what we have as the integrand here. So this is just a good check to do whenever you're computing an integral. Then we see that evaluating this, we get negative 2 times, well, it's t to the negative 1/2, so it's 4 to the negative 1/2, or 1 over 2, or rather 1 over 4 to the 1/2, minus 1 over 1 to the 1/2, which is equal to negative 2 times 1/2 minus 1, which is equal to 1. So the answer here is E. Next, let f be the function defined by f of x is equal to the square root of the absolute value of x minus 2 for all x. Which of the following statements is true? Well, we know that this function, so the square root of x is plotted as the following. It's plotted as this function. Then we know that the absolute value of x is plotted as this function. So there's a kink at x is equal to 0 here, meaning it's not differentiable at this point. So, if we combine these two, we can see that the square root of the absolute value of x is equal, it's plotted as the following. We have the usual square root of x, and then since x is equal to negative x here because of the absolute value, we just take the mirror image of this. So we see the usual kink at x is equal to 0, which is not differentiable. And when we have a negative 2 here, so x minus 2, this just gets shifted to the right. So with the x minus 2, it doesn't change anything about the kink here. It just shifts the whole thing to the right by 2. So we know that it's not differentiable at x is equal to 0. But when you look at this plot, it's certainly continuous. There's no jumps or discontinuities at all. So we know that the answer cannot be B because it's certainly not differentiable. We know that it's continuous. So here this is x is equal to 0. And that means that the square root of x minus 2, the square root of the absolute value of x minus 2 is plotted as, like I was saying before, you just shift it to the right, where this point here is x is equal to 2. So we know that it's continuous at x is equal to 2, but it's not differentiable. So B and C are not correct. Then we know that the limit of f of x as x goes to 2 is certainly 0. It goes to the x-axis, which is the y is equal to 0 value. So D is not correct. We know that there is no vertical asymptote here just by looking at the plot. So the answer here must be A. Or that f is continuous but not differentiable at x is equal to 2. Moving on, the points -1, -1, and 1, -5 are on the graph of a function y is equal to f of x that satisfies the differential equation dy dx is equal to x squared plus y. Which of the following must be true? Well, we wish to see whether or not it's a local minimum, a local maximum, or a point of inflection. The way that you find this is by taking, well, firstly, we need to find that at all of these points, we know that dy dx is equal to 0. So firstly, we need to check which of these points, if any, satisfies this equation. Plugging in, we find that if we plug in for 1, -5, this thing is equal to 1 minus 5. So this is not equal to 0. But, because 1 minus 5 is equal to -4, which is not 0. But, and just to clarify, this is for 1, -5. If we have dy dx is equal to 0 for the point -1, -1, if we plug in, we get x squared, so -1 squared, or 1. So I can just write -1 squared minus 1. And this is equal to 0. So -1, -1 has dy dx is equal to 0. So that's good. We can already get rid of A and B. Then we look at what it means to be a local maximum, a local minimum, or a point of inflection. Well, this point, the local maximum, is satisfied when d squared y over dx squared is less than 0. And that's because d squared y dx squared less than 0 means it's concave down. So it looks like this, meaning this point here is a local maximum. Similarly, d squared y over dx squared is greater than 0 for a local minimum. And finally, for a point of inflection, d squared y over dx squared is equal to 0. So we just have to compute d squared y dx squared and then plug in for -1, -1, and see which of these cases is satisfied. Doing so, we find that d squared y dx squared is equal to 2x plus dy dx. And this is equal to 2x, plugging in for the dy dx up here. This is equal to 2x plus x squared plus y. And evaluating this at -1, -1, this is equal to -2 plus -1 squared minus 1, which is equal to -2 plus 1 minus 1, which is equal to -2. So this is less than 0, meaning we have a local maximum. So the answer is C. Moving on, what is the radius of convergence of the series given by the following? Well, to compute the radius of convergence, recall that we first need to find what is AN. This is just the nth summand. So here, this is equal to x minus 4 to the 2n over 3n, or 3 to the n. So that's just the summand for a generic n value. Then we need to compute the following. We need to compute the absolute value of a n plus 1 over an. And this is the absolute value of x minus 4 to the 2n plus 2 divided by 3 to the n plus 1. And you multiply this by the inverse of an. So this is 3 to the n over x minus 4 to the 2n. And simplifying this, we can cancel the 2n here with this 2n, and then the 3n gets canceled with this 3n. So we're left with the absolute value, or since this is a positive quantity anyways, I'll get rid of the absolute value. So this is equal to x minus 4 to the 2, because that's the only term in the exponent that is left, and we divide by 3. So to compute the radius of convergence for a series, you first compute this, and then you say that you want it to be less than 1. So we then find that the absolute value of x minus 4 is less than the square root of 3, just by multiplying 3 over and then taking the square root. But this 4 here doesn't change the result of the sequence. So the radius of convergence would be the same if this -4 were instead a 0, or like plus 0, or if it were -1,000 or plus 1,000. It doesn't matter. It doesn't change the radius of convergence. So this square root 3 here is the actual radius of convergence. So we find that the answer is C. Next, we wish to find which of the following is a logistic differential equation, where k is a positive constant. Generally, we know that the logistic differential equation is given by the following. dy dt is equal to ky times 1 minus y over r, where here, this is a logistic differential equation is often used to model population growth. So here, k is often called the growth rate. So this is often called the growth rate. And r here is often called the carrying capacity. And the reason for that is this r, the carrying capacity, is the amount that a population can sustainably have and maintain. So if you wanted to model the amount of geese that could live in a certain area, and you knew that only 100 geese were possible, then you can model how quickly they grow and how many geese there are as a function of time by solving this differential equation, also knowing the growth rate. So how many geese are born each year. But looking at each of these equations, we see the only one that satisfies this equation, or is similar to this equation, is E, where R in E is equal to 1. So the answer here is E. Moving on, the graph of a differentiable function f is shown above. It's shown here. If h of x is equal to the integral from 0 to x of f of t dt, which of the following is true? Well, if we look, we're integrating from, we're trying to find h of 6. So we're going from 0 to 6. So we don't care what happens after 6, because we're finding the integral of f of t, where this thing here is f of t, and the integral is just the area under the plot. So we don't care what happens after 6. Then, plotting the first and second derivatives of f, we see that the first derivative of f is given by the following. We start at the maximum value, because this is like a sine graph, and this seems to be the maximum slope. So we start here, and then the slope at this point, roughly x is equal to 2, is 0. So this needs to quickly die down to 0 at x is equal to 2. So we look something like this. Then we have from 2 to 6, we have a growth. We have a growth that looks something like this. Where here, at this point, we have the maximum value. So making this a little neater, we have the maximum value here. And then it doesn't matter what happens after 6, so I won't even draw it. And then taking the derivative of, so this blue is f prime of t, and then taking the derivative of this to find f double prime, we find that, well, firstly, we start at 0 because the slope here is approximately 0, and then the slope is increasing along this part of the graph. So we increase from 0 to 2. So we increase here, and then the plot starts to decrease, and it goes to 0 at x is equal to 6. So we look something like this. And again, it doesn't really matter what happens after this point. And here, the purple line is f double prime of t. So what we wish to do is we wish to find the areas underneath each of these plots. So firstly, we note that the purple has only positive area. So that's something important to note. Secondly, this black plot here, which I'll shade in yellow, so I'll just draw over f with yellow. This is all a negative area. Finally, this area of f prime looks just like this area of f prime, but from 0 to 2 we have a negative value of the area, and from 2 to 6 we have a positive value of the area. And the reason that I say that these look similar is that, well, if we look at each of them, we have on the left here, we have something that goes lengthwise 4 units, and widthwise it goes 2 units. Whereas here, we have something that goes widthwise 4 units, so from 2 to 6, and then lengthwise it goes 2 units. So these two areas are exactly equal to each other, except one of them is negative and the other is positive. So we see that the plot of f of t is all negative. So that will be the smallest value. So we can get rid of everything that doesn't have h of 6, because that's the derivative, that's the integral of f of t as the smallest. So we get rid of these because h of 6 is not the smallest. Then we look at, so we note that h prime of x is equal to the integral from 0 to x of f prime of t dt. So, and similarly, h double prime of x is equal to the integral from 0 to x f double prime of t dt. So, the integral of f prime of t is approximately 0, whereas the integral of f double prime of t, the purple, is positive. So, h double prime of 6 is greater than h prime of 6. So the answer here should be A. Next, let y equals f of x be the solution to the differential equation dy dx is equal to x minus y, with initial condition f of 1 is equal to 3. What is the approximation for f of 2 obtained by using Euler's method with two steps of equal length starting at x is equal to 1? Well, we note that Euler's method is given by y of n plus 1 is equal to y of n plus h times f of xn, comma, yn, where here h is given to be the step size. So how large are your steps? And f is equal to y prime of xn. So it's the derivative of y evaluated at xn. So let's do the method. Well, we know that we're starting at x is equal to 1, and we're going to 2, because we want to approximate f of 2, where 2 is the x value. So going from 1 to 2 for x with 2 equal steps, so 2 steps of equal length. Well, if we want to take 2 steps of equal length from x is equal to 1 to x is equal to 2, we see that h has to be 0.5. Then we see that y of 1.5, because we're starting at 1 and we want to approximate the y value at 1.5, which is the step value, or the step size. So this should be equal to y at 1, which is just f of 1, plus h, which is 0.5, times dy dx. So dy dx here, we know that at x is equal to 1, y is equal to 3. So we have x minus y, or 1 minus 3. So this is equal to, well, y of 1 is equal to 3, and then we add 0.5 times 1 minus 3, which is negative 2. So this should be equal to 3 minus, well, the 0.5 times 2, that's equal to 1. Then we have a negative, so 3 minus 1, which is 2. Doing the last step of Euler's method, we see that y of 2, we take another half step. So this is equal to y of 1.5 plus 0.5 times, well, what is the x value? Because we want to, what are the x and y values? Because we want to plug in here dy dx. So the x value here is given by 1.5, because that's the old x value. And then we subtract the old y value, which is y of 1.5, which we computed to be 2. So, computing this, we have, well, y of 1.5 is 2, and then we add 0.5 times 1.5 minus 2. Well, 1.5 minus 2 is negative 0.5. So the answer here is 2 minus, and then 0.5 times 0.5. That's equal to a quarter, or 0.25. So that the answer here, so this is 2 minus 0.25, and that's equal to 1.75, or 7/4. So the answer here is C, 7/4. Next, for x is greater than 0, the power series 1 minus x squared over 3 factorial plus all of this converges to which of the following? Well, we see that, let's consider the first three. You should automatically see that this power series looks very similar to a trigonometric power series, because we know that sine of x is because we have a generic value here for a generic n. So we know that sine of x is equal to the sum from n is equal to 1 to infinity of x to the 2n plus 1 over 2n plus 1 factorial times negative 1 to the n. And if we divide by x here, we get this 2x to the 2n, but it leaves all of these things intact. So we see that the answer should be sine of x divided by x, because if we divide by x, so dividing by x, we get rid of this 1 up here. And that's exactly what we have here. So the answer should be sine of x over x, or C. Next, the graph of f prime, the derivative of a function f, consists of two line segments in a semicircle, as shown in the figure above. If f of 2 is equal to 1, then what is f of negative 5? Well, let's first compute the areas under this plot from x is equal to negative 5, which is here, to x is equal to 2, which is here. Well, we have first a negative area given by half of a semicircle. So we know that the area of a circle is pi r squared. So half of a semicircle would be 1/2 times pi times r squared. The radius of this semicircle is 2. So this is 1/2 times pi times 2 squared, which is equal to 2 pi. Then we have a positive area here. And this is given by, well, it's a triangle, so the area of this here is 1/2 times the base, so the base is 3, times the height, which is 2. So this is equal to 3. Then we know that if f of 2 is equal to 1, then f of 2 should be equal to f of negative 5 plus the integral from negative 5 to 2 of f prime of x dx. And that's because if you take this integral from negative 5 to 2, the total area here, which is the integral, should give you the amount of f that has accumulated from negative 5 to 2. So if we have what we started with at negative 5, and then we add all that's accumulated from negative 5 to 2, we should get f of 2. So rearranging this, we get f of negative 5 is equal to f of 2 minus the integral. So the integral from negative 5 to 2 of f prime of x dx. And plugging in, we find that we know that f of 2 is equal to 1, and we subtract this integral. So this integral is the signed area underneath this plot from negative 5 to 2. So that should be 3 minus 2 pi. So the answer here is equal to 2 pi, because the negatives cancel, and then 1 minus 3, which is negative 2. So 2 pi minus 2. So the answer here is A. Moving on, the function f is defined by f of x is equal to x over x plus 2. What points xy on the graph of f have the property that the line tangent to f at xy has slope 1/2? So we want the slope, or f prime of x, to be equal to 1/2. But we know that f prime, just using the quotient rule, is equal to the denominator, so x plus 2, times the derivative of the numerator, which is 1, because we're taking the derivative with respect to x. And then we subtract the numerator x times the derivative of the denominator. The derivative of the denominator is 1. And then we divide by x plus 2 squared, or the denominator squared. So this is equal to 2 over x plus 2 squared. Then, manipulating this equation, we get that x plus 2 squared is equal to 4, which implies that x plus 2 is equal to, taking the square root, this is equal to plus or minus 2. The plus or minus is important here, because when you take the square root, you get two solutions. So, this is solved by x is equal to 0 and x is equal to negative 4. So, f of 0, plugging in here to this f value above, we get that f of 0 is 0 over 0 plus 2, or 0 over 2, which is 0. Then, f of negative 4, plugging in, we get negative 4 over negative 4 plus 2, which is equal to negative 4 over negative 2, which is equal to 2. So, we actually have 2 points at which the slope has value of 1/2. Firstly, at 0, 0. Then, at negative 4, 2. Because this f value gives us the y value on the graph. So the answer is 0, 0, and negative 4, 2. So the answer is C. Next, let's compute the following integral. Well, we see that we have two polynomials, and since the polynomial in the denominator is second order, we know that we can separate this into two different terms. That is, we know that x squared plus 3x plus 2, well, if you complete the square, this is equal to x plus 2 times x plus 1, which implies that 5x plus 8, which is the numerator, divided by x plus 2 times x plus 1, this should be equal to 2 over x plus 2 plus 3 over x plus 1. So, the integral now has two terms, because we've rewritten the integrand as two different terms. So, the integral in question is now the integral from 0 to 1 of 2 over x plus 2 dx plus the integral from 0 to 1 of 3 over x plus 1 dx. Then, solving these integrals, we see that we can just use natural log. So this becomes 2 times the natural log of x plus 2, evaluated from 0 to 1, plus the integral, plus 3 times the natural log of x plus 1, evaluated from 0 to 1. And solving for these, we see that this is 2 times the natural log of, well, plugging in for 1, this is the natural log of 3, minus 2 times the natural log of 2, because we plug in for x is equal to 0. Then we add 3 times the natural log of x plus 1, where x is equal to 1, so this is the natural log of 2. And then we subtract 3 times the natural log of x plus 1 where x is equal to 0. But that's just the natural log of 1. But we know the natural log of 1 vanishes. So that goes away. Then we see that the answer here, looking at each of these, is the following. Well, we have two terms that have the natural log of 2. So we can add these together, so we get 3 ln 2 minus 2 ln 2. That's just equal to ln 2. So the answer here is 2 times the natural log of 3 plus the natural log of 2. But we then recall the log rules. The log rules say that when we have a coefficient, we can actually bring it into the exponent of the argument. So this is equal to the natural log of 3 squared, because we just bring the 2 up to here. And then we add the natural log of 2. But further, when we add two logarithms together, this is actually the same thing. So 3 squared is 9, so I'll put 9. This is actually the natural log of their arguments multiplied together. So it's 9 times 2, which is equal to the natural log of 18. So the answer here is C, the natural log of 18. Moving on, the line y is equal to 5 is a horizontal asymptote to the graph of which of the following functions? Well, let's just plug in for x is equal to 5 for each of these. A horizontal asymptote means that the function at x goes to infinity looks at something like this. Looks like if you have this plot, and this is y is equal to 5. A horizontal asymptote means that you have a function that looks like this. It gets closer and closer to y is equal to 5 as x goes to infinity, where this here is x. So looking at each of these, we know that it's not going to be b, because b is just a linear function. It goes up forever. Similarly, c is not the answer, because although you have some weird behavior at x is equal to 5, that's actually not what we're concerned with. We're concerned with y is equal to 5. So this plot doesn't have a horizontal asymptote. Plugging in for y is equal to 5 here, we actually don't get any weird behavior as x goes to infinity, because when we take x to infinity here, this just goes to -1. Similarly, c goes, if we take x going to infinity, this goes to 0, because the bottom blows up. And 5 times x, as x goes to infinity, that goes to infinity itself. And the answer for A, if we take x goes to infinity, this dies off and goes to 0. So the only answer left is E. But looking at what we have for E, if we take x goes to infinity, we see that we don't care about this term. We don't care about the negative x term. And when x goes to infinity, we can actually cancel the x squared and the x squared. So we get 20 over 4, which is equal to 5. And that's exactly what we wanted as an asymptote. So the answer here is E. Next, the power series given by the following converges at x is equal to 5. Which of the following must be true? Well, we know that if we plug in for x is equal to 5, we know that the sum from n is equal to 0 to infinity of a n times 2 to the n converges. So, we wish to find which of the following is true. For all of these, for most of these, we don't have enough information about an. So if we plug in for each of these, if we plug in for x is equal to 0, we get an times negative 3 to the n. And we're taking a sum of that. But we actually don't know if that converges or diverges. We don't have enough information about an. The same is true for x is equal to 1, converging or diverging. So B and C are also not possible because we just don't have enough information. Because when we plug in for x is equal to 1 for both of these, we get the sum of an times negative 2 to the n. So we don't know if we allow this to alternate from positive to negative, whether or not it converges or diverges. We only know that this is true. Similarly, we know that that E is not true, because if we plug in for x is equal to 6, we get an times 3 to the n. But again, we don't have enough information. We don't know if that's true. So the only answer left is when we plug in for x is equal to 2. And when we do that, we get a sum, which is given by an times negative 1 to the n. So we know that an times 2 to the n converges. So if we get rid of this weight, because this makes an larger, it makes each element of the summand larger. If we get rid of this and we just allow this to alternate, it's reasonable to guess that that would converge. And in fact, it does. So the answer here is D. And again, the answer is D simply because we don't have any information about any other weights besides negative 1. Moving on. If P of t is the size of a population at time t, which of the following differential equations describes linear growth and the size of the population? Well, linear growth, so linear growth here, that implies that P of t, the population is a function of time, goes as t. So which of the following differential equations, when solved, gives us P of t goes as t? Well, to solve for P of t, we just integrate each of these with respect to t. Doing so, we know it can't be b, because if we integrate b, we get t squared. Similarly, if we integrate c, we get t cubed. And if we integrate d or e, we don't get exactly what we wanted. We'll get, for d, we get some exponential. And if we integrate e, we get something that goes as 1 over t. So that's not what we wanted. What we do want is a, because when you integrate this, you just get P of t is equal to 200t plus some constant. So the answer here is A. Next, let f be a differentiable function such that the following holds. Which of the following could be f of x? Well, immediately we notice that this takes the form of integration by parts. So it takes the form of integration by parts. Then we see here that we need some function that goes as x to the 4th, or at least x to the 3 power. We're not sure which one yet, if you forget how to do integration by parts. So we know that a and b are both wrong. Then recall that this value here should be f prime of x. So it's not c either, because it has to be something that goes as x to the 4th. And recall, for integration by parts, that we need the sign. We usually have the sign in front of the integral to be a minus. So if it's not a minus, then we have the minus coming from some other term. So it either comes from the f term, the f prime term, or from the cosine here. So recall, the integral of sine of x dx is equal to negative cosine x. And then integration by parts would tell us that this integral here, so f of x times the sine x dx, this should be equal to negative f of x cosine x minus f prime of x times negative cosine x dx. Well, the negatives here cancel, and we have a positive plus sign here. So f prime of x has to be positive, meaning f of x has to be positive. So the answer here is E. Next, we wish to solve the following integral. Well, we see that we have an x in front of the e to the x minus x squared. So what we can do is we can do u substitution. So we can use u is equal to x squared. This implies that du is equal to 2x dx, which implies that x dx is equal to 1/2 du. So we have an x here and a dx here. And we've already used that u is equal to x squared. So the integral becomes 1/2 e to the minus u squared du. And we need to change the bounds of the integral. So before we had x is equal to 1, plugging in x is equal to 1 means that u is also equal to 1. And x goes to infinity. Well, x squared as x goes to infinity is still infinity. So the bounds are actually the same. Then, this should be a 2. This should be a 1. There we go. Then, taking this integral, we get that this is 1/2 times minus e to the negative u, evaluated at 1 and infinity. Well, plugging in for infinity and 1, we get that this is negative 1/2 times e to the minus infinity minus e to the minus 1. E to the minus infinity goes to 0. So the answer here is the negatives cancel. So it's 1/2 times e to the negative 1, or 1/e. So the answer is 1/2e, or B. Then, what is the slope of the line tangent to the polar curve r is equal to 1 plus 2 times the sine of theta at theta is equal to 0? Recall that dy dx, the slope of the polar curve, is equal to dr d theta times the sine of theta plus r times the cosine of theta. And you divide that by dr d theta times the cosine of theta minus r times the sine of theta. Here, we note that dr d theta, for this r value, the 1 goes away because it has no theta dependence. So this is equal to 2 times the cosine of theta. Then, plugging in for theta is equal to 0, we get that this is, well, dr d theta at theta is equal to 0 is 2 times the cosine of 0, which is 2. So we get 2 times the sine of 0, which is 0, plus r times the cosine of theta, where theta is equal to 0, and that's 1. And then we divide by dr d theta, evaluated at theta is equal to 0, which is 2, times the cosine of 0, which is 1. And then we subtract r times 0. And it's 0 because we have the sine of 0, which is 0. So, getting rid of the extra terms, this becomes r/2. So what is r at theta is equal to 0? Well, plugging in for theta is equal to 0, this term goes away. So we get r is equal to 1. So this is actually 1/2. So the answer here is B. Next, for what values of P will both series, so both of these series here, converge? Well, let's look at each series individually. We know that this series converges for, well, we know that it will converge so long as 2p is greater than 1/2. I'm sorry, is greater than 1. So we see that p just has to be greater than 1/2. That's all we need. And this sequence converges so long as it's a geometric sequence. That means that the absolute value of p is less than 2. So we know that this here gives us that -2 is less than p is less than 2. And this here gives us that p just has to be greater than 1/2. So if we need both of these to be true, that's when both of the series converge. We see that p always has to be less than 2, and p has to always be greater than 1/2. So both of these converge so long as 1/2 is less than p is less than 2. So the answer here is C. Finally, let g be a continuously differentiable function with g of 1 is equal to 6 and g prime of 1 is equal to 3. What is the following limit? Well, let's plug in for x is equal to 1 for this limit. When we plug in, we see that the denominator is equal to 0 because we get g of 1, which is 6 minus 6. And then the numerator, we have the integral from 1 to 1, and that's always equal to 0. So we get 0 over 0. This implies that we can use L'Hopital's rule. So we take the derivative of the numerator and the denominator. When we do that, the limit now becomes the limit as x goes to 1 of, well, taking the derivative of the numerator is just g of x, and the derivative of the denominator is g prime of x. So we can now plug in for x is equal to 1, so we get g of 1 over g prime of 1, and that's equal to 6 over 3, which we're given in the problem. So 6 over 3, that's equal to 2. So the answer here is D. So this concludes the no calculator section of this part of the exam. So let's move on now to the calculator section. The function f, whose graph is shown above, is defined on the interval -2 is less than or equal to x, which is less than or equal to 2. Which of the following statements about f is false? So as a note here, for the calculator section, you often don't need a calculator. You will for some of the problems, but not for all of them. This problem is an example of one where you don't need a calculator. So let's just look at the graph. We see that at x is equal to 0, this graph is certainly continuous. There's no discontinuities. So we know that A is wrong. Next, looking at B, we wish to answer whether or not f is differentiable at x is equal to 0. But looking at x is equal to 0, we see that this is not differentiable because there's a kink. So the derivative coming in this way points down, whereas the derivative coming in from this way, from the right, points this way. And since these aren't equal to each other, this is not differentiable. So we've already found which statement is false. That is B. Next, let f and g be the functions given by f of x is equal to e to the x and g of x is equal to x to the 4th. On what intervals is the rate of change of f of x greater than the rate of change of g of x? So as a note here, I've provided this plot This is not a plot that the exam provides, but we wish to answer on what intervals is f prime of x, so the rate of change of x. So we wish to find when is f prime of x greater than g prime of x. But f prime of x is just equal to e to the x. And we wish to find when is e to the x greater than g prime of x, which is 4 times x cubed. So I have f prime and g prime plotted here. Then we wish to find when is the blue curve greater than the orange curve. Looking at these, we see that this occurs after this location, which is approximately 7.5, and it also goes all the way to infinity. So any value greater than 7.4, 7.5, 7.3, any x value greater than that satisfies this inequality. And we also have, for x goes to negative infinity, this is true. So we have negative infinity and positive infinity being x values which satisfy this inequality. So the only plot here the only interval here which has negative infinity and infinity, but also does not contain these this orange shaded region, where the orange plot is actually greater than the blue plot, is B. So the answer here is B. Next, the graph of the piecewise function f is shown above. What is the value of this integral? Well, firstly, let's find the integral of f of x from -1 to 9. This should be given by the area, the signed area, underneath this plot. So it's going to be the blue minus the orange. So the blue area is equal to, well, it's a triangle, so it's 1/2 times the base of the triangle, which is 6, times the height, which is 2. So this is equal to 6. Then we wish to find the orange area. And this is equal to, well, it's, firstly, we can decompose it into a triangle. So if I erase this, we firstly have a triangle here. And that triangle is given, it has an area of 1/2 times the base, which is 1, times the height, which is 1. And then we can add this rectangle. So the area of this rectangle is its length times its width, or 1 times 3. So we add 1 times 3. So the answer here is 1/2 plus 3, or 3.5, or 3.5. Then we find that the integral from -1 to 9 of f of x dx is equal to 6 minus 3.5. So this is equal to 2.5. Then this integral here, the integral from -1 to 9 of 3 times f of x plus 2 dx, this is equal to 3 times the integral from -1 to 9 of f of x dx plus the integral from -1 to 9 of 2 dx. Well, we already computed this integral, so this should be equal to 3 times 2.5 plus 2 times 9 minus -1. Evaluating this, we can use our calculator. So this is equal to 7.5 plus 20, which is equal to 27.5. So the answer here is C. Next, let f be a function having derivatives of all orders for x greater than 0, such that f of 3 is equal to 2, f prime of 3 is equal to negative 1, f double prime of 3 is equal to 6, and f triple prime of 3 is equal to 12. Which of the following is the third degree Taylor polynomial for f about x is equal to 3? Well, firstly, a Taylor polynomial has each x is actually an x minus 3. So we know that a and b automatically are not the answer because it's not a Taylor polynomial. Then we need to look at c, d, and e. Well, let's compute f double prime of 3 for c. F double prime of 3 is equal to, well, taking the two derivatives of this, we see that the first term goes away and the second term goes away because they don't have at least x squared. But taking two derivatives of this term, we get 12. And then the second term becomes, taking two derivatives, it's 72, so plus 72 times x minus 3. But since x is 3 here, this is 3 minus 3. And we know that we wish for f double prime of 3 to be equal to 6. But this term goes away because we have 3 minus 3, and we wish to say that 12 is equal to 6, which it's not. So the answer can't be C. Looking at D now, let's look at f triple prime of 3. F triple prime of 3, well, we know that this term goes away, the second term goes away, and the third term goes away. Then f triple prime here is equal to this is equal to 24. But that's not equal to 12, which is what we wish for it to be equal to. So the answer is not D. So the answer here is E. Next, the graph of f prime, the derivative of the function f, is shown above. Which of the following statements must be true? Well, let's look at each statement in series. For statement 1, we say that f has a relative minimum at x is equal to negative 3. Well, we know that this plot is f prime. So, computing f prime is equivalent to taking the derivative of f. So that means that for whatever function we have here, we have something that has a negative slope, and then it becomes positive. So we have something that looks like this. And then maybe it decreases in its slope, and then it goes up more. So here, we see that at x is equal to negative 3, which is this location here, we in fact do have a relative minimum. So 1 is correct. And it is a relative minimum because we have, if we look at the derivative again, we have a derivative that is negative, and then at some point becomes 0 for an instant, and then becomes positive. And that is the definition of a relative minimum. So, looking at the second statement, we wish to see whether or not the graph of f has a point of inflection at x is equal to negative 2. So x is equal to negative 2 is this point here. And we see that looking at this, the derivative, so a point of inflection occurs when d squared f, it occurs when f double prime is equal to 0. But the derivative here is not quite 0, it's slightly positive. So the answer, 2 is not an answer, it's not true. Then looking at the third statement, we say that the graph of f is concave down for the interval 0 to 4. But looking at this plot, this is the plot of f prime, so it's the derivative of f. So we have a derivative or a tangent line of f, which is positive, and then becomes 0, and then becomes negative. So we have a tangent which is positive, it becomes 0, and then it becomes negative. And this is the definition of concave down. So 3 is also correct. So since 1 and 3 are correct, and 2 is false, we said that the answer here is E. Next, let f be a function that is twice differentiable on the interval -2 to 2, and satisfies the conditions in the table above. If f is an even function, which is what this means, what are the x-coordinates of the points of inflection of the graph of f on the interval -2 to 2? Well, a point of inflection occurs when f double prime is equal to 0. So, at which of these locations is f double prime guaranteed to be 0? Well, we know it's guaranteed to be 0 when we have f double prime going from negative to positive. We know that that's a guaranteed point where we have a point of inflection. So, since this becomes negative to positive at x is equal to 1, we know that x is equal to 1, we have a point of inflection. But the answer here is not A, because, recall, this function is even. So, whatever occurs at x also occurs at negative x. So the answer here should be 1 and -1, or D. Next, what is the average value of y is equal to the square root of cosine x on the interval 0 to pi over 2? Well, recall that the average value of a function, y bar, is equal to 1 over b minus a times the integral from a to b of y of x dx. This is the average value of y from a to b. Here, this is equal to 1 over pi over 2 minus 0 times the integral from 0 to pi over 2 times the square root of cosine x dx. So, computing this integral using our calculator, we get that this is approximately equal to 1.198. So, this should be, well, since pi over 2 minus 0 is pi over 2, this is 2 over pi times 1.198. So, using our calculator again, this is approximately equal to 0.763. So, the answer here is C, 0.763. As a note, the answer is not D. D is just the value of the integral. It doesn't have this b minus a. So make sure you recall this part of the average value equation. Next, if the function f is continuous at x is equal to 3, which of the following must be true? Well, the definition of continuity at x is equal to 3 is the following. The definition says that if f of 3 is continuous, if f is continuous at x is equal to 3, then f of 3 is equal to the limit of x goes to 3 from the left side of f of x is equal to the limit as x goes to 3 from the right of f of x. This is the definition of continuity. Then we see that C says exactly this. So the answer is C. Next, for the interval negative 1.5 to 1.5, let f be a function with first derivative given by this. Which of the following are all intervals on which the graph of f is concave down? Recall that concave down means that f double prime of x, so the graph of f is concave down when f double prime is less than 0. So solving for f double prime, we see that f double prime of x is equal to 4 times x cubed minus 4 times x. And then we multiply by the original exponential. So times e to the x to the 4th minus 2x squared plus 1. Then we can just plot this function on our calculator. Doing so, we get this. So we wish to find, so this firstly is f double prime, and we wish to find when is this less than 0. Well, it's negative from x is equal to 0 to x is equal to 1, and from x is equal to negative 1 all the way to negative infinity. So the interval is, well, we're only concerned with the interval from negative 1.5 to 1.5. So we go from negative 1.5 to negative 1, and then from 0 to 1. So that interval is given by d. So the answer is D. Next, the fuel consumption of a car in miles per gallon is modeled by the following, where S is the speed of the car in miles per hour. If the car is traveling at 50 miles per hour and its speed is changing at the rate of 20 miles per hour squared, what is the rate at which the fuel consumption is changing? So the rate at which the fuel consumption is changing is given by miles per gallon per hour, which is why all of these answers are in those units. Then we note that the units of f prime of s is equal to, well, f of s is the fuel consumption, or miles per gallon. And then if we take the derivative with respect to s, then we divide by miles per hour. So this should be miles per gallon divided by miles per hour. Then we wish to get from this answer to something that's in terms of miles per gallon per hour. The way to do this is to multiply f prime of s times something that is the rate of change of the speed. So if we multiply this by miles per hour squared, then we find that the answer here is miles per gallon divided by miles per hour times miles per hour squared. These miles cancel. This hour cancels with 1 hour here. So this is equal to miles per gallon per hour, which is exactly the units that we want. So we need to calculate f prime of s, and we need to find the rate of change of the speed. We're given the rate of change of the speed is 20 miles per hour squared. So this is 20. So all we need to do now is find f prime of s at 50 miles per hour. So at s is equal to 50. Doing so, we see that f prime of s is equal to 1 over 20 minus s over 1200 times 6 times e to the s over 20 minus s squared over 2400. Then, using our calculator, we can plug in for s is equal to 50. So f prime of 50 is equal to 0.215. And again, that's just from the calculator. Then, the true answer here, as we said before, is f prime times 20, which is the rate of change of the speed of the car. So the answer here is 0.215 times 20, which is given by, after plugging into your calculator, 4.299. So the answer here is B. Next, if f prime of x is greater than 0 for all real numbers, and the integral from 4 to 7 of f of t dt is equal to 0, which of the following could be a table of values for the function f as given above? Well, let's look. For a, we see that all of the values here of f of x are below the x-axis. So although between 4 and 5 it could go above the x-axis, it's not given in the table. And all we're looking for is a possible table for f of x. So since all of these are below the x-axis, it's not likely that the integral of f of t dt from 4 to 7 is 0. It's actually more likely that this integral is less than 0. Since all of the f values are below the x-axis, the area between the plot and the x-axis should be negative, or less than 0. So we know that this is not an answer. Next, let's look at C. Looking at C, we find the rate of change from 4 to 7. Doing so, if we go from 4 to 7, we see that f of 5 is actually less than f of 7. This implies that f prime of x is less than 0. But we're given that f prime of x is always greater than 0. So C is not an answer. Next, for D, we see that all of the f values are 0. Although that doesn't mean that every single f value is 0, it means that this table has only zeros. So if we're only to assume what f looks like from the table, we would have to guess that f prime of x is equal to 0. But we know that f prime of x is greater than 0, not greater than or equal to 0. So this is also not a valid answer. Finally, looking at this table, we have that all of the f values are above the x-axis. So it's likely that the integral from 4 to 7 of f of t dt is greater than 0. Well, we know that this integral should be equal to 0. So E is not a valid answer. And the only valid answer here is B. And that's because we have some values below the x-axis and some values above the x-axis. So it's likely that this integral is 0. And we see that for all of these values, the derivative is greater than 0. So all of these values are constantly increasing. So the answer here, again, is B. Next, let R be the region in the first quadrant bounded by the graph of y is equal to the natural log of 3 minus x for the interval 0 to 2. R is the base of a solid for which each cross-section perpendicular to the x-axis is a square. We wish to compute the volume of the solid. Well, consider this. We know that the plot of this function looks something like this, right? Maybe it's flipped along the x-axis, actually. But either way, what we want to do is we wish to find, the plot actually here looks something like this. right? Yeah, it looks something like this. Then what we wish to do is we wish to compute the volume of a solid whose base is given here and whose cross sections, so cross sections going this way, are squares. So that means whatever this length is, that's how tall the solid is, the volume is at that x value. So the integral here of the volume is equal to, so v, the volume, is equal to the integral from 0 to 2, because that's the interval we're concerned with, times the natural log of 3 minus x squared dx. And we're squaring it because we wish each of these gives us the area of a sliver of this volume. So we take a square of the natural log because we know that each cross section is a square. So it's length times width, which is the area of a square, and each side length is this natural log. So plugging in this integral into our calculators, we find that the answer is 1.029. So here the answer is B. Next, the derivative of a function f is increasing for x is less than 0 and decreasing for x is greater than 0. Which of the following could be the graph of f? Well, let's just plot the derivative of each of these functions. We see that this derivative here for a is firstly negative, and then it's increasing to 0, and then it's decreasing, and then it's increasing again. So this here is an always increasing derivative. So it's not decreasing for x is greater than 0. So A is not a possible answer. Similarly, for B, we see that the derivative here is firstly large, and then it gets smaller until it becomes 0, and then it continues to get smaller and becomes very negative. So the derivative here is always decreasing. So this is also not an answer. Next, looking at this derivative, we see that it's firstly 0, and then it becomes negative, becomes very negative, and then it begins increasing back to 0. So we have 0, and then it decreases, and then it increases again. But this is the exact opposite of what we want. So C is not the answer. Next, we have for D, we have a tangent which is very large and positive, and then it decreases to 0, or not to 0, to something that's small, and then begins increasing again. So this is another always increasing derivative. So this is not decreasing for x is greater than 0, so it's not the answer. Finally, looking at E, we have something which is very negative, and then increases, and then decreases again to become more negative. So we have something that increases for negative x and decreases for positive x, which is exactly what we wanted, so E is the answer. Next, a particle moves along a line so that its acceleration for t is greater than or equal to 0 is given by the following. If the particle's velocity at t is equal to 0 is 5, what is the velocity of the particle at t is equal to 3? Well, we note that a of t, the integral from 0 to t of a of t prime dt, this is equal to v of t minus v of 0, because the integral of the acceleration is the velocity. But this is also equal to the integral from 0 to t of t prime plus 3 over the square root of t prime cubed plus 1, because that's what we're given as a of t. So v of t is equal to v of 0 plus this integral. So plus, but now plugging in for t is equal to 3, we find that v of 3 is equal to v of 0 plus the integral from 0 to 3 of t prime plus 3 over the square root of t prime cubed plus 1 dt prime. Then, solving for this integral on our calculators, we find that it's 6.71, and v of 0 is given to be 5. So the answer here is 5 plus 6.71, or it's equal to 11.71. So the answer here is 11.71, or E. Next, if the series an converges and an is greater than 0 for all n, which of the following must be true? Well, let's look at each one in series. For a, we're simply not given enough information about a of n to say that this is true. We need more information about it, besides that the sum over all an's just converge. Moreover, this b is also not true because this is only true for geometric sums, but we're not given that this is a geometric sum. We're just given that it's a convergent sum. So it's not true in general. Next, C is impossible because a of n for all n is greater than 0. So the sum over positive numbers cannot be equal to 0. So C is impossible. Next, D, we're simply not given enough information for. We can't tell because, if an is equal to 1 over n cubed, then n, the sum over this, still converges because we would have, this would be equal to the sum over 1 over n squared, which we know converges. So we're not given enough information to say that D is correct. And this leaves that E is the correct answer. And this is certainly true because we know that an converges and that 1 over n goes to 0 as n goes to infinity. So we're actually decreasing the value of each term in the summand by adding this 1 over n. So it just makes it a more convergent sequence, or a more convergent series. So the answer here is E. Next, the figure above shows the graphs of the polar curves given by the following. What is the sum of the areas of the shaded regions? Well, we know that the entire region here is equal to just the area of this circle, which is since it has a radius of 2 as given here, it has an area of pi times 2 squared, which is equal to 4 pi. Then we wish to find the area of this this blue shaded region here. But we recall that the area of a polar curve, so the area that a polar curve traces out, is given by the integral from alpha to beta, where alpha and beta are angles. This is, so it's the integral from alpha to beta of 1/2 times r squared d theta. Then this is equal to the 1/2 times the integral from 0, because we're starting at 0, and we go to pi, and we multiply by r squared. So r here is 2 cosine 3 theta. So this is 4 cosine squared times 3 theta, d theta. And the reason that we use pi is that we trace out 3 of these loops. So if we went all the way to 2 pi, At 2 pi, this would be 3 times 2 pi, which is 6 pi. So that would trace out 6 of these loops. But we only want to trace out 3 of them. So we do pi, because when we plug in for pi to theta, we get 3 times pi, which is 3 of those loops. So, using our calculator for this integral, we see that this becomes 1/2 times 2 pi, which is equal to pi. So, the shaded region here is equal to the orange area minus the blue area, which is pi. So the answer here is 3 pi. And plugging 3 pi into our calculator, this gives us d. Finally, the function h is differentiable, and for all values of x, h of x is equal to h of 2 minus x. Which of the following statements must be true? Let's look at each statement in sequence. For statement 1, it says that the integral of h of x from 0 to 2 is greater than 0. But this is not true, because we can always come up with a counterexample. And the counterexample here, so as an example, consider the following plot, where this is 2, this is 1, and this is 0. Consider the plot given by this. This agrees with h of x is equal to h of 2 minus x because it's symmetric about x is equal to 1. But this is a purely negative function here. So the integral is actually negative. So it's not true that the integral is always positive. So 1 is not correct. Next, we know that, next let's look at 2. H prime of 1 is equal to 0 is the statement. We know that h of x is equal to h of 2 minus x means that we have a function which goes up, or it does something from 0 to 2. So if this is 2, this is 1, this is 0, we have a function which does something, and then at 1, it just goes back down and does the same thing that it did before, but mirrored. Now, we could say, what if the derivative were not defined here? But we are given that the function h is differentiable, so the derivative has to be defined. And because we're going in one direction and then we swap and go in the opposite direction, we see that the derivative at 1 has to be 0. So this is in fact correct. Then, looking at statement 3, the statement is that the derivative at 0 and 2 is equal to 1. But this is certainly not true because we have no criteria on the derivatives at the endpoints. All we're given is that the derivative at 1 has to be 0. There are no other requirements on the derivatives anywhere except that they exist. So 3 is just simply not necessary. It's possible, but it's not necessary, just like 1. So the only answer here is 2. So the answer is B. And with this, we conclude my answers to the AP Calculus BC 2012 Practice Exam Multiple Choice section, as given by the College Board. Thank you.